Hello guys, this is Himanshu from Code Campaign and we are continuing with our binary tree module. So today we are going to discuss about the diagonal printing of the binary tree. In the previous video we discussed about the left view and the right view of the binary tree, and the video before that we discussed the bottom view of the binary tree and the top view of the binary tree. So today we are going to discuss about how to print the diagonal diagonal view of the binary tree. Now let me show you something. You guys might have got bored by seeing all these videos of different type of view printing, right? But I want to show you something here. So this is the question from Geek for Geese, right? Diagonal traversal of the binary tree. So if you go down here, you can see this question is being asked in Paytm, Amazon, and if you go on career curve and search, you can see like this question is recently being asked in Microsoft interview as well. So whatever problem we are discussing here, even though there are too many problems of printing the different views of the binary tree, but these all problems are very important, and you can be asked any of these problems in your interview. So if you master these, and most of the times, at least in Amazon interview I have observed, you will get one problem related to binary tree printing, and many of my colleagues were used to ask the top view of the binary tree or the vertical order printing of the binary tree. So if you master all these problems whatever we have discussed up till now, you will surely be able to get one question in your interview regarding the printing of the tree, and you will be able to easily handle it. So okay, so let's go back to where we started. So diagonal printing of the binary tree. So prerequisite video is again vertical order traversal. If you haven't watched it, I will recommend that you pause the video here, go back, watch the vertical order traversal, and then come back and watch this video again. Okay, so what does the diagonal traversal of the binary tree or the diagonal view of the binary tree says? So suppose we have this diagonal and then this diagonal. So if we need to do the traversal on our binary tree, um, if we have to do the traversal in our binary tree according to this diagonal, so the output will start from here. So 1, then 3, then 7, then 2, 5, 6, 8, and then 4, right? So this will be our output. Okay, so if you observe here, we are traversing traversing in alignment to this diagonal, right? So we will traverse in this direction, so that's why 1 3 7. Then we will traverse in the direction of this diagonal, so 2 5 6 8, and then we'll traverse in this direction, so 4. Okay, so now let's see one more example. So suppose this is our example, so let's again draw the diagonal here. So these are our two diagonals. So what will be the output? We'll traverse in this direction, so 1 3 7 9, 2 5 6 8 10 11 12 and 4. So this will be our diagonal traversal of the binary tree or diagonal printing of the binary tree. Okay, so let's go ahead and see how we are going to implement this or how we are going to solve this problem. Okay, so suppose this is our given binary tree. Let's draw our diagonals again. Okay, so let's suppose, let me just change the pointer here. Okay, so let's suppose the height of this node is 0. Okay, so if you see here, if we traverse in line with this diagonal, the height of all these right children remains same. So the height of this will again be 0. The height of this will again be 0. And whenever we will move towards the left child, the height will increment. So the height of this will be 1. And this is the right child of, oh, this is the left child of this. So its parent height is 0. So this will become plus 1 again. We'll add 1 here. And and s- okay, so we have the left child. Now, as this 5 is the right child of this, so this height, the 5 height will remain same as of 2, so this will again be 1. And 6 is the 8 is the right child of 6, so the this height will remain same, as the right child will always have the same height. And now again we are moving towards left, so we will add 1 in to our parent child, so this will be 1 plus 1, 2, right? Okay, so now if we collect all the nodes which have the similar height, so our output will be the node which have this height 0 are 1, 3, and 7. The node which have height 1 are 2, 5, 6, 8, and the node which have height 2 is 4. And if you go back here, so this is our diagonal view. Okay, so okay, so this is the logic. If whenever we are moving towards the right, or whenever we are calculating the height of the right children, it we will keep it as the same of the height of the parent, and whenever we are calculating the height of the left children, we will increment it by 1. Okay, so now let's go ahead and see how we can implement it. So as you already know, so what we are going to use, as we use in vertical order traversal, we'll use one queue. And as we are dealing with heights again, so we will use one map, right? So we'll use one again sorted dictionary, and the key will be the height or the distance, and the value will be the list of tree nodes. This is the same thing that we did in our vertical order traversal as well. Okay, so we'll start from here. Let's put our first node into our queue and its height, which is 0. Okay, so now what we'll do, we'll pop our first element from the queue, which is 1, and then we'll check if the key exists into the 0 key exists into the sorted dictionary or not. So it doesn't exist, so we'll enter. Okay, now we'll put its left and right child into the queue. So the left child, for the left child, what we were doing for the left child, first we'll put the node, and the height will be parent's height plus 1. So parent height is 0, so this height will be plus 1. Okay, now we'll put the right child. So let's put the right child, and height will be same as its parent, so it will be 0. Okay, now we will again uh, take the element from the front of the queue, which is 2. So we'll again check if 1 as a key exists into our sorted dictionary or it doesn't exist. So we'll insert 1 here, and then we'll put our node 2 here, and then we'll put its left and right child into the queue. So 2's left child is 4, and its height will be as 2's height is 1, so its height will be 1 plus 1, which is 2. And then we'll put its right child, which is 5, and this height, the height of 5 will remain same as height of 2, which is 1. Now we'll again pop the element from the front of the queue, which is 3. Again we'll check if 0 key already exists in this map or not. So it already exists, so we'll add 3 here. Okay, now we'll check, now we'll add the left and the right child of the 3 into the queue. So the left child is 6, and the height of 3 is 0, so the left child height will be 1, and the right child is 7, and the height of 3 is 0, so the right child height will also remain same. Okay, now we will pop the next element from the front of the queue, which is 4. So we'll again check if 2 as a key exists into our sorted dictionary or not. So 2 doesn't exist, so we'll add 2 here and put 4 here. Now we'll check if there is any left or the right child of 4. uh, so there is no left or right child of the 4, so we'll not do anything. We'll extract 5 from the queue. So we'll again check if the 1 as a key exists in here or not. So 1 exists, so we'll put 5 here. And then we'll check if 5 has any child that we can push into the queue. So it doesn't have, so we will extract the next element, which is 6. And then we'll check if 1 as a key exists into the sorted dictionary. So it does exist, so we'll add 6 here. Now we'll check if 6 has any left or right child into the queue. So it doesn't have left child, but it has the right child, so we'll insert it into the queue, which is 8. And the height will be same as 6, so we'll say 1. Now we'll pop the next element, which is 7. And then we will check if 0 as a key exists into our map or not. So 0 exists, so we'll put 7 here. Now we'll check if 7 has any child that we can push. So it doesn't have anything, so we'll pop the next element, which is 8. And we'll check if 1 as a key exists into our map. So it exists, so we'll push 8 here. And we'll check if 8 has any child that we can push into our queue. So it's not there, so we'll not do anything. Now our queue is empty, so we'll print the output of the sorted dictionary. So the output will be 1, 3, 7, 2, 5, 6, 8, and the last one is 4, right? And this is the same diagonal traversal that we wanted to produce. So I hope now you understood how to implement the diagonal traversal of the binary tree. So now let's go ahead and write the code. Okay, so this is where we left our ID in the last video, where we write the right view and the left view of the binary tree. So in this video we are going to write the diagonal traversal. So let's go back up and copy the vertical order traversal code. So again, you will see here whatever we have learned in the previous videos is sufficient enough to write this, to write the to write the code for the problem of diagonal traversal with a very minimal change. And if you haven't watched the video of the vertical traversal and directly watching the diagonal traversal, I will highly recommend you go back and watch the vertical order traversal video and then come back here. Okay, so we just changed the name, and after that the only thing that we need to change here, right, up. So if we go back here, the everything that we do in the vertical order traversal is same with the diagonal order traversal, apart from this part where, so in the vertical order traversal, what we were doing, we were changing, we were so our right children used to have the distance of parent plus 1, and the left children used to have the distance the parent had minus 1, right? So if you, it would have been the vertical order traversal, then 3 distance would have been plus 1 and this distance would have been minus 1. But in diagonal traversal, what we are doing, we are keeping the right child distance as same, and the left child distance we are incrementing by 1. So let's go back here and change this part. So here if you see the left child distance we are decrementing, so what we have to do, we have to increment it by 1, and the right child distance will remain same as it was for the parent. So that's all. This is what we have to change, and the apart from it the whole code will remain same. So that's just a 2-line change. Now we'll go back here and let's comment our, and let's call our function whatever we wrote, check, and check if this thing works. So yeah, that's all. So easy. Now let's run our code. Okay, so this is the traversal that we printed. Now let's go back to our slide and just bring our output here. So at least we will be able to compare. Okay, so let's compare. Let's put it here. So let me drag it a little bit. Cool. So now let's compare. So 137, 137, 2568, 2568, 4, 4. So that means our diagonal traversal works. So what will be the time complexity for this algorithm? The time complexity will remain same as it was for the vertical order traversal. So the time complexity will be n log n. If you don't understand it, please go back and watch the video where I explained the time complexity. I will explain it again. So the for as we are inserting all the elements one by one into the sorted dictionary, and the sorted dictionary takes for addition of the element and for the addition of the element log n time, and we are inserting n elements here inside, so the time complexity will be n log n. If you don't understand it, we watch my previous videos, you will understand it. And the space complexity will be equal to O of n, because we are using the queue, and in worst case scenario we will store all the elements into the queue. So the time complexity will be n log n and the space complexity will be O(n). Uh, uh, so that's conclude our video. If you haven't subscribed to my channel, please go ahead and subscribe to my channel. And if you like this video, please give it a thumbs up. If you have any comments, please put it into the comment box. I will reply. So that's all for this video. I hope you enjoyed my video. Thank you.